Our next speaker then will be Joshua McDuffie from the New Mexico Institute of Mining and Technology, discussing mechanical properties of coatings made by dry aerosol deposition of lunar regolith simulant. Joshua, are you here?
Yes, I am.
Very good.
And
Floor is
for
yours.
sake of bandwidth saving, my internet's not too stable. I'm going to keep my camera off. Um, Hello everyone. My name is Josh McDuffie, and today I'm going to be talking about my research exploring the mechanical properties of ceramic coatings made by dry aerosol deposition of lunar regolith simulant. Next slide, please. So a little bit of an outline. I'm going to go through the goals and objectives for this project, and then a short introduction to dry aerosol deposition, or DAD, as I'm going to refer to it for the rest of the talk. And then I'm going to get into my experimental results, the conclusions of that, and then ongoing and future work. Next slide, please. So the goal for this project was to provide proof of concept for using DAD of lunar and Martian regolith as a viable SIRU in space manufacturing process for applications including in situ system repair, micrometeorite protection, thermal barrier coatings, and possibly dust mitigation coatings as well. The objectives were to deposit dense nanocrystalline ceramic films onto space-relevant materials using DAD with lunar regolith simulant as our feedstock powder. I also set out to characterize the mechanical characteristics of these films using a Nanovia PB1000 nano indenter and scratch tester. And I also would like to demonstrate the impact resistance of the coatings using a novel kinetic impactor. Next slide, please. So a little bit about dry aerosol deposition. It's a relatively new additive manufacturing process that we use to deposit robust, dense ceramic coatings onto various substrates without the need for thermal consolidation. Any binding materials or water is not necessary for this process. On the left is a rough illustration of our setup here at New Mexico Tech. We have a roughing and a booster pump that reduces our vacuum pressure in our chamber to around 2 torr. So these films are sprayed in a rough vacuum. We use a vibration stage as well as a nitrogen gas supply to create a fluidized bed of our powder to aid in the aerosolization. And then on the right, you can see an illustration of how the powder actually consolidates on the substrates through a convergent diverging nozzle is the one we typically use to decrease the bow shock of the gas stream onto the substrate. This illustration also shows the necessity for the proper particle size distribution of the powder, as larger particles will impact and erode the surface, causing massive craters, as well as finer particles will just follow the gas stream out to the sides and not consolidate on the sample itself. Next slide, please. So the feedstock powder that we use is called LMS1 from Exolith Labs at the University of Central Florida. The mineralogy can be seen on the top left, as well as the particle size distribution chart in a percent finer on the top right. The rings and stars are our experimental data for our dry and wet sieves that we have conducted. And for our purposes, particle size is required to be under 53 microns. So the bottom left SEM image is of the newest batch that we have received, sieve fraction to 53 microns, not milled. So we took it out of the bag, sieved it, and then put it under SEM. The second one on the right is more of a milled sample. So we milled it at 300 RPMs for 4 hours in a planetary mill. And also was sieve fractioned to 53 microns. You can see that there's a modest particle size reduction in the larger particles, but the number of fines stays consistent. Next slide, please. A little bit about the characteristics of these films. The top left is a electron microprobe low mag image of one of the surfaces of one of our films, showing that the surface is essentially pinhole free and continuous throughout the length of the film. The top right is a SEM image of the cross-section of one of the films, showing the compactness of the films as well as the density. And for sake of time, I didn't have the ability to add an AFM image of our films, but the microstructure from those images was around on the nanoscale. The bottom three films were sprayed previously by one of my colleagues and one of my co-authors on this project, Robert Calvo. The bottom left is a 26 micron thick film on steel. The middle is on Kapton tape, and the left one is our most recent and thickest film to date, which was 32 microns on 5mm Kapton. Next slide, please. These three samples are the ones that I specifically tested for this project so far. So we have a 19 micron thick film on steel on the top left. Bottom left is a 4 micron film on glass. And then the top right is a 26 micron film on aluminum. Right of that image is a picture from our Zygo surface profilometer showing the step height of the film compared to the substrate being the blue on the left, and then the red and yellow itself is the film. The line plot corresponds to that surface profilometer image, showing that the average thickness of the film throughout was about 26 microns. Next slide, please. So here we can see a graph from our Nanovia nano indenter on the aluminum sample. The black lines are the individual tests on the substrate itself that had a standard deviation of about 0.25 over 15 tests, and then the red lines are individual tests on the film itself. The tables below, the colors correspond to the colors in the graph. So the red is going to be the film data, and then the black is the substrate. You can see in the left table the hardness values for the films across the three substrates were relatively similar, which means that the tests that we conducted were indicative of the ceramic film itself and did not depend on the substrate beneath. Steel and aluminum were both approximately double the hardness on the film than the substrate, and glass was about half, which was to be expected as silicate glasses are harder than metals. The reduced moduluses are also relatively consistent with mixed silicates ceramics, as they are harder, but they have more of a give in their
2 minutes, Josh.
Okay. Next slide, please. I also conducted scratch tests on the aluminum and the steel samples with loads of 1200 millinewtons for each. The substrates scratched at for the aluminum was about 3.43, and the steel was about a gigapascal harder, which was to be expected. The films, however, the LMS1 film on aluminum was polished up to 0.5 microns using a diamond slurry, which removed the surface characteristics of the films, which are cratered and significantly rougher than the bulk of the film, which gives it a higher resistance to abrasion. So that film did not scratch. The LMS1 film on steel, however, was tested as sprayed, and so we did get a scratch out of that as the surface was rougher and more susceptible to abrasive damage. The scratch hardness on the film for the steel sample was still about a gigapascal harder than the substrate itself. Next slide, please. A couple conclusions from this. We used LMS1 to create thick, dense films on space-relevant substrates, including glass, aluminum, steel, and Kapton. The films increased the hardness of the surface on the aluminum and the steel, but decreased the hardness of the glass surface. The film hardness, regardless of the substrate, and the reduced elastic modulus are in the ranges of 3.5 to 4 gigapascals and 65 to 70 gigapascals, respectively. These films have been shown to have high scratch resistance, especially in the bulk of the film. And the DAD of Lunar Regolith shows potential as protective coatings for softer and more susceptible materials. Next slide, please. So a little bit of future work. I'm going to conduct more extensive scratch and hardness tests on films of differing thicknesses to see how the thickness depends on the actual characteristics of the film itself. And I'm also going to use these films to test the impact resistance of hypervelocity impacts just using a microparticle accelerator that the New Mexico Tech Material Senior Design Team created in the past year. Image of that can be seen on the bottom left with the movable sample stage, a vacuum pump port on the back, and then a detonator mounting plate for using RP3 detonators to accelerate the particles on the front. The bottom right is a image of one of their successful tests last semester of an impact event of a silicon carbide particle on acrylic. And I will be aiming to also use their data to test the films for impact resistance of mine. Next slide, please. That's all I have today. Thank you for having me. And are there any questions?
Thanks, Joshua.